This video is about an incident that occurred in one of our projects at the Center for Water Informatics and Technology at LUMS. The title of the video is Adjusting Message Transmission Rate for Power Conservation at the Namal Dam, Mianwali. I will begin by first describing the project. The Mianwali district is situated in northwest Punjab and is the seat of Namal Valley, where the Namal Dam is situated. The dam was constructed in 1913 during colonial rule for the primary purpose of irrigating the surrounding arid lands. Today, the dam is deeply integrated in the lives of the local population through many socio-economic and cultural activities. Flooding is a major issue for the Namal Dam and its surrounding population. Especially in the monsoon season, heavy rainfalls occur and the streams leading to the reservoir are filled at an alarming rate. In the pictures, you can see the effects of the flood from 2015. Here is a graphic describing the reservoir and its inflows. The inflows to the reservoir happen through three major tributaries. There are three major hill torrents, Rikhi, Tarappi, and Golar, which feed the rainfall occurring in the catchment area to the dam. Here is a picture of the Tarappi Nala taken from one of its bridges. You can see that the Nala is majorly dry and that very little water is flowing inside of it. This picture was taken in the summertime, just before the monsoon season. A striking feature of these nalas is that when rainfalls do occur, especially during the monsoon season, these torrents fill up at an alarming rate. Now I will show a video from the same location taken during the monsoon season. Here is the same stream which is being viewed from underneath the bridge, and you can see how much water is now inside of the stream. Now, a very important feature of these flows is that because the catchment area is so large, that rainfalls occurring at one part of the catchment are not visible at other parts. So for instance, when rainfall occurs in the upper catchment area, the locals at this bridge do not anticipate that a huge flow of water is headed towards their way. This effect can be observed very clearly through these pictures. These pictures were taken from a single location in the monsoon season of 2019, and the stream that is visible is the same Nala, Tarappi. Now just before these pictures were taken, the stream was dry and people were carrying out their excavating and sand digging activities. Now as you can see, the weather is sunny, and even though rainfall was occurring in the upper catchment hilly area, the locals had no idea, and when the flow of water came, it came so suddenly that the locals did not even have time to take out their tractor trolley. And even though the locals saved themselves, they could not save their excavating vehicles. And a heavy loss occurred, which could have been avoided if they had a beforehand warning of the torrent of water coming their way. In order to address this issue, the Center for Water Informatics and Technology has initiated a project in the Namal Valley. In this project, we will be placing sensors at various locations in the catchment area to measure rainfall so that a warning of incoming floods can be broadcasted to the locals in order to save heavy damages. Now, this incident is about a sensor, that we had placed exactly at the dam of the Namal Lake reservoir. Here you can see pictures of the sensor as it has been installed at the dam. This sensor sends us information about the level of water inside the lake, any rainfall that is occurring, temperature and humidity of the ambient atmosphere. Here you can see the different components of the sensor. As you can see, the sensor has a rain gauge which records the level of incident rainfall. It has some electronic circuitry to take the measurements and record them, and a battery which is used to keep the circuit operational. The sensor also has a solar panel through which the battery is charged, and it also has an antenna which is used to transmit the measured data. Thus, there are two types of operations that discharge the battery. The first operation is the recording of measurements, and the second operation is the transmission of the recorded measurements to a back-end server. The battery consumption can be represented by the variable we call state of charge. This is the same indication that you get on your mobile phones to represent how much your battery is consumed. Now, if the measurements are being taken constantly on the sensor, then the state of charge follows a certain type of behavior, which is simply a decaying exponential. Now, this can be represented mathematically through a first order model where beta represents how frequently the measurements are taken and recorded. Note that we have not yet talked about the effect of the charging circuitry. Now, let us see the effect that the charging circuitry has on the state of charge of the battery. First of all, let us see how solar energy behaves over the duration of time. So first of all, during daytime, when the sun is out, the incident solar energy on the battery's solar effect increases until nighttime is reached, when it starts decreasing, and then the sun is out, it starts increasing again, and this cycle repeats with a 24-hour time period. Now we can also represent this energy through a forcing function which we will call L, and this represents the luminosity that is reaching the solar panel. Now the state of charge is affected both by the natural discharge due to the recording of measurements and the luminosity of the solar energy. Now let us see how both of these terms, which are given in blue and yellow respectively, affect the behavior of the state of charge over time. Now we can see that as the luminosity is increasing, the state of charge also increases until it reaches a maximum value. And when the luminosity decreases, it only discharges and it reaches subsequently the maximum value again. And it continues this behavior in periodic fashion. Now you may have observed that the graph of the state of charge is flat from the top, and this actually represents the maximum charge of the battery. So the charge cannot go over 100% even though the luminosity is at its maximum value. The last operation that is taking place on the sensing unit is that of the transmission of the recorded data. Now let us represent this by the variable capital T, and the form of capital T is as visible right now on the screen. So whenever a data packet is transmitted, the transmission term takes on a positive value only at that time instant. And as we will see, this will result in a sudden discharge of the battery. And when the transmission is done, this term goes back to being zero. So we arrive at the final equation for the behavior of the state of charge. Now, the state of charge is decreased by the taking of measurements. It is increased by incident solar energy, and it is also decreased by the transmission of data. Now let us see how the state of charge behaves under normal operation of the sensing unit. Pay careful attention to both the functions capital L and capital T as time is progressing. So we start from here. The luminosity is increasing, the state of charge is at its maximum value, behaving accordingly, and boom, a measurement was transmitted and a sudden discharge happened. And again, so we observe another sudden discharge in the battery. Again, a sudden discharge we have observed due to the transmission of data. And the same thing happens whenever a transmission takes place. So you can see that the transmission has a greater effect on the discharge of the battery as the measurement. Right? And whenever the transmission takes place, a sudden spike in the battery is observed. Now, the incident that we mentioned in the beginning of the video was related to the sensor that was installed at the lake. And the incident was the development of a particular fault in the charging circuit, so that even though there was a particular luminosity acting on the solar panel, the battery was not discharging in the best way. So let's see what would happen if the charging of the battery is not being done as it should be. So the behavior progresses in the same way. However, the charging is less. Now a packet was transmitted, and you will observe that before the second packet is transmitted, the battery was not able to be charged fully. And once the second packet was transmitted, the discharge in the battery was such that it just reached a very low level and then it never got up again. And this is because when the second packet was transmitted, because the charging was not done completely, the charge of the battery finished. And once the battery discharged, the sensing unit shut off completely. And even though there was some luminosity that was acting on the solar panel, the data was not being recorded. And this can result in the loss of valuable data, especially in critical applications such as the flooding that we had just mentioned in the beginning of the video. Now, in reality, we are constantly monitoring the health of our sensors, and whenever such a problem is encountered, such as the one just described, we take steps to address that problem. And in this particular case, what we did was that we adjusted the rate at which data was transmitted so that the battery had ample amount of time to charge, even though the charging was happening very slowly. This we can do in our sensors with the sending of an SMS. Let us see how we were able to save our battery by adjusting the transmission rate of the sensor. Now, the behavior that we observed was the same that we discussed in the previous case. So a message was transmitted, and here we observed that when the transmission of the message happened, the battery dropped precariously close to the minimum level. Now, if we had not adjusted the transmission rate, then the next message would have been transmitted at this point. So what we did was we anticipated that if the message is going to be transmitted at the time that was determined by the last transmission rate, the battery will go dead. So what we did was that we increased the transmission rate to push the transmission of the message even further to give the battery more time to charge. And then we observed what happened. Now the message transmission occurred, and as we can see, the battery had charged sufficiently enough that it did not die down to zero when the transmission took place next. And as you can see, at this new transmission rate, the uh, battery had time to charge so that our measurements reached us and there was no loss of valuable data. Now note that this is not a permanent solution because it is not possible for us to continuously keep on monitoring the sensor. So it is very easy to miss a malfunction. There are on-board circuits and even a small computer which is adjusting the transmission rate of the sensor, keeping the state of charge into perspective, so that whenever the battery goes close to dying down, the transmission rate is decreased. Now, what happened in our case was that we replaced the sensor with a spare unit, but till then we had to do the adjustment manually. Now I also want to highlight that whenever you are increasing the rate of transmission, or if you are decreasing the rate of transmission, you are losing valuable information at that time instant, which is getting delayed. So if a flood or an event of interest happens between that time of transmission, so that event will not reach us until the packet is transmitted. So to stay informed, we need a higher rate of transmission, but to conserve our battery, we need a lower rate of transmission. And this is something that we continuously adjust, keeping in view our application of the sensing technology. So I hope you learned something from the video. Thank you for watching.